Algebra 2. Today we're going to talk about graphing exponential functions and logarithmic functions. I'm using Desmos a lot for the graphs, and you may also. I don't need us to graph things by hand on graph paper if we don't need to, so take that as your advantage. First of all, opening exercise. Complete the following table of values of the function f of x equals 2 to the x. We want to sketch the graph of y equals f of x and then reflect that graph across the diagonal line with the equation y equals x. Hold on. We can calculate all of those numbers, or I just copied the answers over onto this slide just for our benefit, and then go ahead and graph what we see here. In Desmos, I went ahead and graphed y equals 2 to the x. I also graphed y equals x. And then the last thing, this right here is the line of reflection. And then I graphed x equals 2 to the y, which is actually the reflected line. Sorry, I had to sneeze. This is the reflected line, so let's look at it. So what we see here is the original y equals 2 raised to the x power. It's an exponential function. Here's the linear line. That's funny, linear line, y equals x. So the blue line is reflected over y equals x, and it becomes the orangey yellow line. And this is the reflected line, which I can graph as x equals 2 to the y. If you go anywhere on this line and draw a perpendicular line through the line of reflection, you'll find the same point on the reflected line. So perpendicular, those two lines are equidistant away from the center. Perpendicular. So you can graph those yourself, and you could graph this whole line all by yourself if you just found points on one graph, draw perpendicular line through. I forgot where I was going on this one. There we go. And you can find the points on the other graph, or the other line, I'm sorry. Cool? So that's how your line of reflection is made. Or you can switch the x and y's and solve for x. Something I'd like to point out is something I see on standardized tests or the fun competition tests that we do. If I take any point, and let's take point over 2 up 4. Let's take point 2, 4. We'll call it P. And I want to reflect this point over the line y equals x. I'm actually going to get point Q, which is 4, 2. Let's test it. So over 4, up 1, 2. Right? Let's take point A, which we're going to do 1, 2, over 1, up 2. So we're going to reflect it and call it B, and that's going to be over 2, 1. So that is common for a reflection over the line y equals x. Okay, let's try our first exercise. Complete the following table of values of the function g of x equals log base 2 of x. We want to sketch the graph of y equals g of x and then reflect that graph across the diagonal line with the equation y equals x. Ta-da! We have the xy values that we would use to graph. I'm going to use Desmos, and I'm going to graph y equals log base 2 of x and y equals x. And then I'm going to reflect it. I'm going to reflect y equals log base 2 of x over the diagonal line y equals x. And I'm going to get x equals log base 2 of y for my reflected line. And there we go. Just like the last example, if I draw line segments that are perpendicular to this line of reflection, all of the intersection of the line segment and the points are equidistant from the line of reflection. So you can graph these by hand if you would like, or you can take a line segment, especially where you have an ordered pair, draw a diagonal, and you'll get your new ordered pair. So you can pick a few and draw a curve. Because these are all going to be perpendicular to your diagonal line. Cool? Alright. Just like the previous example, I can take points like A and B. A is ordered pair 0, 1. B is reflected over the diagonal and is going to be point 1, 0. C and D. C is ordered pair 1, 2. Reflected over the diagonal y equals x, and I'm going to get D, which is 0.21. Okay, they're all going to work like that, no matter what point you find. If I find E, what should F be? E is 2, 4. F is going to be 4, 2. Very cool. So I can say for any point, a reflection of any point, comma, AB, over a line y equals x is point BA. The next thing we're going to look at is actually, we're going to look at graphs of the functions f of x. Let's get that cleaner. F of x equals 2 to the x, and let's say g of x equals log base 2 of x are reflections of each other over the line y equals x. Okay, that's the next thing we're going to look at. But before we do that, we can actually use our logarithm rules that tell us why, that explain why f of x equals 2 to the x and g of x equals log base 2 of x are reflections of each other. So let's talk about that for a second. So we're actually going to look at points. We're going to look at point AB on the exponential graph and point BA on the logarithm graph. So if point AB is a point on the exponential function, we have x and y. We can say that b equals 2 to the a, correct? Then I can change that into logarithmic form by saying log base 2 of b equals a. So if here we have ab equals xy, we went ahead and substituted a into x and b into y if we're graphing it, because f of x is y when you're graphing. And here they flipped orders. So if we're graphing it, that's our y and that's our x. So that's how they reflect over the line y equals x. Cool? Well, that was pretty cool. So for example, or for exercise 2, the classwork says working independently. Yay, we're all working independently. Predict the relation between the graphs of the functions f of x equals 3 to the x and g of x equals log base 3 of x. Test your predictions by sketching the graphs of these two functions. Write your prediction in your your notebook. Provide justification for your prediction and compare your prediction with that of your neighbor. I graphed them in Desmos. No need to predict. I've got the exponential function, which is always going to be above the x-axis, and the logarithm function, which is the reflection of it. Because this is base 3 and this is an exponent of 3, they will reflect each other over the diagonal y equals x. So your prediction, if you made it, was correct. Now let's compare the graphs of the functions f of x equals 2 to the x and f of x equals 3 to the x. Sketch the graphs of the two exponential functions on the same set of axes and then answer the questions below. Before I move on to the next slide, let's see what we notice. I see they intersect right here. They change places. And let's see what the questions say. Where did the two graphs intersect? I circled that. They intersect at 0, 1. For which values of x is 2 to the x less than 3 to the x? So where x is greater than 0, 2 to the x is less than 3 to the x. For which values of x is 2 to the x greater than 3 to the x? Where x is less than 0, 2 to the x is greater than 3 to the x. If we look at this first example where x is greater than 0, 2 to the x is less than 3 to the x. So 2 to the x is below 3 to the x, so it is less than. And then for values less than 0, 2 to the x is greater than 3 to the x. It's above it. These next few questions talk about what's called end behavior. So, well, let's just look through it. What happens to the values of the functions f sub 2 and f sub 3 as x approaches 0? So what we do is we look at the x-axis, which I have not put on this drawing. Awesome. So let's sort of add it. So that's the x-axis. Alright, so what happens to the values of the functions f2 and f3 as x approaches infinity? So if we look just where x goes to infinity, so I'm just following the end behavior. As x goes to infinity, what is happening to the functions? As x goes to infinity, both functions go to infinity. So that's what we're looking at. As x does something, what is y doing? Cool, so let's write that down. And it's pretty fancy how we write it. As x approaches infinity, f of 2 of x approaches infinity, that's the y value, and f of 3 of x also approaches infinity. What happens to the values of function f2 and f3 as x approaches negative infinity? So now we're just looking at it this way. As x approaches negative infinity, what's happening to the y's? Well, the y's are approaching 0. As x approaches negative infinity, f2 of x approaches 0, and f3 of x also approaches 0. Does either graph ever intersect the x-axis? No, it doesn't happen. For every value of x, we know that this cannot equal 0 because 2 raised to the 0 power is 1, 3 raised to the 0 power is 1, so neither one of those will ever reach a 0. Okay, number 4, add sketches of the two logarithm functions g2 of x equals log base 2 of x, and g3 of x equals log base 3 of x to the axes on the graphs of the exponential functions from exercise 3. So in exercise 3, we had these. These were given, or we made these in exercise 3. I just graphed these on the same x and y axis, and here's what the color means. So y equals 2 raised to the x power has a partnership with y equals log base 2 of x, and y equals 3 to the x power and log base 3 of x sort of match up. The blue and the yellow and the red and the green. So take a look at these, sketch it if you'd like. We're going to talk about them with the next few questions. So where do the two logarithmic graphs intersect? They intersect right there at 1, 0. For which values of x is log base 2 of x less than log base 3 of x? Where x is less than 1, log base 2 of x is less than log base 3 of x. Let's look at that. So here, x is 1. So when x is less than 1, your yellow is greater than your green. Your yellow is greater than your green. Or your green is less than your yellow. So green is less than yellow. The further we get away, the smaller the numbers get, right? It's backwards. So when x is less than 1, log base 2, which is green, is less than log base 3, which is yellow. For which values of x is log base 2 greater than log base 3, where x is greater than 1, log base 2 of x is greater than log base 3 of x. Now let's look at the end behavior. What happens to the values of the functions g2 and g3 as x approaches infinity? As x goes this way, what happens to the values of the functions g2 and g3? As x goes to infinity, both g2 of x goes to infinity and g3 of x goes to infinity. These values are just going to keep on getting more and more and more. They're going to increase as x approaches infinity. And then as x approaches 0, as x goes in this direction, your y values are approaching negative infinity. So that's approaching negative infinity as x approaches 0. So in a fancy way to say it, as x approaches 0, g of 2 of x approaches negative infinity, and g of 3 of x approaches negative infinity. Does either graph ever intersect the y-axis? Explain how you know. No, they don't. We can't define logarithms for negative values of x. Okay, log of a negative x just doesn't work. You can't define it. Describe the similarities and the differences in the behavior of f of 2 of x and g of 2 of x as x approaches infinity. As x approaches infinity, f of 2 of x approaches infinity and oh goodness, sorry, g of 2 of x also approaches infinity. Okay, you have both of them approaching infinity. That would be similarities. Differences. If you look at the exponential function, it gets large pretty fast. It increases quickly. and the logarithmic function increases very slowly. That's actually it for the lesson today. This is what we're doing in class tomorrow. I'll take out some of the graphing problems or direct you to use Desmos, but it should be pretty okay. Good job.